things. First of all, you're to build the model. We'll look at those here in just a bit. Reminder that the last day to withdraw is Tuesday, April 17. If you are concerned about your status in this course, you should talk to me. There is an extra credit opportunity. I have not posted it up there yet on D2L. It's called an egg experiment because it's one that involves using an egg. It's going to take 3 days. This will be one that is worth 2 points. I don't offer much extra credit in here, but this will be one opportunity. You'll see a drop box for it, just like you see the drop boxes for your other labs. It is due before you take experiment 4 or exam 4. Exam 4 is going to be on D2L, and if you start taking exam 4, it's going to lock out that drop box. So if you want to have the chance for extra credit, you have to submit it before you take exam 4, or the drop box is not going to be available. Again, that would be on or before April 26th. And just like on previous labs, you do need to provide your proof of completion. You'll see a place for some photos or whatever else on there. So any questions on any of these items? All right, next up we have our Socrative app questions. Let's take a look at these really quick. We'd like to know which types of carbon-to-carbon bonds are the only type present in saturated hydrocarbons. Those are single bonds. Those are single bonds. Next up, when referring to saturated hydrocarbons, what is it that they are saturated with? I don't know that we actually mentioned that in this class last week, but just in case we didn't, and we probably didn't, what it is that they're saturated with here is hydrogen. So if you didn't get that, that might be one of those things you write down. This here is an example of a saturated hydrocarbon right here. All of the carbon-to-carbon bonds are single bonds. This one here is unsaturated, which means it has something other than carbon-to-carbon single bonds. If we were to open this up, that means we can put in more hydrogen. And if we look at the next question in here, the next question actually was along those same lines. Unsaturated hydrocarbons must contain at least one of these two carbon-to-carbon bonds. Select both types. They are double or triple. So again, if we open this bond up here, we can fit in more hydrogen into it. If we have a carbon-to-carbon triple bond, we can open these up and we can fit more hydrogen into it. So when we say that they are saturated, what it is that they are saturated with hydrogen. We can't physically get any more hydrogen in here if all we have is carbon-to-carbon single bonds. So any questions on this piece about saturated and unsaturated? All right, next up, the correct condensed structural formula of octane is, very good. Next up, this here is the line formula of octane, very good. And if we have an alkane with 20 carbon atoms, correct formula is, very good. So I guess the biggest piece we missed, and I think it's because we didn't have quite enough time last week, was the distinction between saturated and unsaturated. So again, just remember that piece. If it's saturated, all the bonds are single bonds, and it is saturated with hydrogen. So with that, today, what we're going to do is we are going to move on from here. And we had a packet last week. In fact, we had 3 different handouts, and unfortunately, my other class used up all my handouts yesterday, so let's get out those packets, and in there we should have had 3 pieces. One of them here was this fold-out packet right here. We're going to write on that today. Then we had these rules for IUPAC nomenclature. Get these out. We'll be going through these today. And then there was a worksheet. Thank you very much. Then there's a worksheet. We may or may not go through these today. If we do go through these today, this will be done at the very end of the class period. This will be when we'll be working on these kind of an open scenario. So we will be working on this packet today. We did work on the front page in here on Friday of last week. And so we completed everything there. Today then, what we're going to do, and let's just see if I have this here. There we go. If you fold it open, then we're going to work on the second page in here today and work on naming some of these. And we are going to be using the rules for nomenclature that we had started here last week. So remember now, when we work with these rules of nomenclature, these rules are applied in order. We work down top from bottom when we assign names and write out formulas. So since we work top to bottom, let's go ahead and work through some of these names. I know it's been a week. We'll try here again. First thing we're going to do is we're going to name this one right here. And if we follow through our sequence of steps on these, it says the first thing we're going to do is to identify and name the parent chain. And recall that the parent chain is the longest consecutive chain of carbon atoms in the molecule. So as we look at this, how many carbon atoms are in this parent chain? There are 7. So we count through 1, 2, 3, 4, 5, 6, 7 right here. Not only do we identify it, but we name it. What is a 7-carbon alkane called? Heptane. Exactly. So we write that name down. Then the next thing we're going to do, according to the rules, is we're going to identify and name all branches of the parent chain as alkyl groups. And again, we talked about how the alkyl groups are named last week. An alkyl group is an alkane that has had 1 hydrogen removed, blah, blah, blah. So if we come back here, how many branches are there off of this parent chain? There's 2. So I have 1 here and 1 here. Now I know that these are obvious, but this is just all a part of our review. How many carbon atoms in this chain with this branch? There's 1. How many carbon atoms in this branch? 2. If I have a 1-carbon branch, a 1-carbon branch is called a methyl group. And it's called a methyl group because the way we name it, according to our conventions, is this is an alkyl group is named by changing the A and E suffix of the alkane to a suffix of YL. So if a 1-carbon alkane is called methane, a 1-carbon alkyl group is called a methyl group. This one here has 2 carbons in it. A 2-carbon alkane is called? Ethyl. Right, it's called an ethyl group. So this here is a methyl group, this here is an ethyl group. If we had a 3-carbon branch, it would be called a propyl group. Exactly, and a 4-carbon branch would be? Butyl, right, so it's butane, so it would be called a butyl group. So again, we count the number of carbon atoms in those branches. So if this here is an ethyl group, and this here, methyl group, and this is ethyl, then we need to come down here and see what it says to do next. Next, it says to locate and assign a number to the position of each branch off the parent chain. And in this case, we have multiple branches off the parent chain, so we're skipping down to here where we have multiple branches. We're going to count in the direction that gives us the lowest branch for any number off the parent chain. So we could count from left to right, in which case we get 1, 2, or from right to left, in which case we get 1, 2, 3. So the direction we're going to count here is going to be left to right. So we count 1, 2, and so I'm going to write these down here. 1, 2, and then we keep counting 3, 4, 5. Once we establish a direction, we keep counting in that direction all the way across. So we get 1, 2, 3, 4, 5, 6, 7 as the numbered positions. So according to this, then, the methyl group is attached to carbon atom number 2 in the chain. The ethyl group is attached to carbon atom number 5 off the parent chain. So then what the rules tell us is this. We keep going down. If we have branches of the same type, we do this, but these aren't the same type. These are different types. So we come down to here, and it says if we have branches of different types, then we say that the alkyl groups are named in alphabetical order, with a number indicating the position of each alkyl group off of the parent chain. So if we were to do these in order, which of these two is going to come first? Methyl or ethyl? Ethyl will come first. Okay? So alphabetically, ethyl comes first. So we're going to write that out here. Ethyl is going to come before methyl. And I'm leaving a space here now between ethyl and methyl. And then according to this, it says that we have a number indicating the position of each alkyl group off the parent chain. And then what we do is we write in that number before the position. So if the ethyl was off of carbon atom number 3, we'd write 3-ethyl. If the methyl group was off of carbon atom number 2, we'd put in 2-methyl. Well, it wasn't 3 and 2. In this case, the ethyl group was attached to carbon atom number 5. So we would say 5-ethyl. And the methyl group was attached off of carbon atom number 2 in the chain, so we would say it is 2-methyl. So then when we talk about the name of this molecule, we would say that the name of this is 5-ethyl 2-methyl heptane. So 5-ethyl 2-methyl heptane. When we write out the names, the conventions we use here is this. First of all, the name of an alkene has no spaces, so we write it out as one word, even if it winds up being super, super long. Secondly, numbers are separated by commas, which we didn't have any numbers next to each other here, but if we did, they'd be separated by commas. Then numbers and letters are separated by hyphens, like we showed here. And whether branched or unbranched, alkenes always have a general formula of CnH2n plus 2. We don't need to worry about this last part here because in this class we're not going to be naming cycloalkanes. But again, what we mentioned here last Friday was that alkanes have this general formula of CnH2n plus 2. If we go back to the things that we named last week, we did see some commas in here. So we had branches of the same type. We show here the comma between the two numbers, and because there were 2 methyl groups, we said it was dimethyl. And again, when the branches are different, then we name them alphabetically. Okay, any questions on this one here? Okay, let's go to the next one. Next one here now, we are going to name. We need to first identify the parent chain. Now be careful in this one here. How many carbon atoms are in the parent chain in this one? 6. So we go 1, 2, 3, 4, 5, 6. It looks like what it ought to be, but it is not 6. There's a longer consecutive chain than 6. So if you can trace through something without lifting your finger, 7, right. And the way you get the 7 is to start down here. You count, you get 1, 2, 3, 4, 5, 6, 7. So if you can trace through a pattern, you can also get 7 another way. It's 1, 2, 3, 4, 5, 6, 7. As long as you can trace through a sequence here without lifting your finger, that's your longest consecutive chain. Now, part of the reason why sometimes we have trouble with this and why we count that longest consecutive chain is, if you remember, when we have these molecules, we tend to draw them out as lines when in reality they're bent, and with single bonds they spin around. So sometimes they could spin around. If you look at it like this, you can see how this loops around. We still have 4 carbon atoms in a row. If I twist this around here, we see it's 4 in a row like this. So this one is kind of like this little piece kind of twisted around and hanging down below, down here. And so again, that is a feature of single bonds and why we always need to count the longest consecutive chain. So if we were to trace through this one, we'd trace through it like this and get the 7 carbon atoms. If we have a 7 carbon parent chain, that parent chain would be called heptane, good. Once we have that heptane, then the next thing we're going to do is we are going to identify and name all of the branches off the parent chain as alkyl groups. So how many branches are there off of this parent chain? There's 1, 2, and 3. So anything that's not a part of the parent chain is considered a branch off the parent chain. If we look at these now, are all of these branches, are all of these alkyl groups the same? They are. Not only are the same, they all have one carbon atom, and a one carbon atom branch is called a methyl group. So these are all methyl groups, and since we have 3 methyl groups, what do we call it? Trimethyl. Exactly, this would be trimethyl. Trimethyl. Then what we're going to do is we're going to count in the direction that gives us the lowest number. So if we count from right to left, we get 1, 2, or from left to right, we get 1, 2, 3. So in this case, it appears we are going to count from right to left. So we'll start counting with this as being the number 1 position. And we'll count 1, 2, 3, 4, 5, 6, 7. Since we've now counted these 7 positions, we'd say that the 3 positions of the methyl groups are, help me out here, 2 and 4 and 5. When we write them in, how do we write them in? With commas. So we put 2, 4, 5. And the way we'd read this is as 2,4,5 trimethyl heptane. So 2,4,5 trimethyl heptane. Any questions on this one? Okay, let's see if what happens if we go in reverse. Next one we're going to go in reverse. So this one here we need to identify the parent chain. The parent chain in here has how many carbon atoms? 6, and we get that because of hexane. So now when I write this out, here's how I go about doing this, going in the reverse direction. I write out the 6 in a row. I don't attach any hydrogens to them yet. So I'd write it like this. I'll center that a little more. There we go. So we got the 6 carbon atoms. Then we need to figure out how many branches we have off that parent chain. So now we have an ethyl group. That ethyl group is going to be attached to carbon atom number 4. So an ethyl group here has how many carbon atoms? 2. So an ethyl group has 2 carbon atoms, and it's going to be attached to carbon atom number 4, is what that's saying. So I come here to carbon atom number 4. We could go off the top or bottom. It's an arbitrary choice. I'm just going to pick the bottom. Okay, so there's my 2 carbon branch. Again, I'm not attaching any hydrogens yet. Then we have dimethyl. So what does dimethyl mean? 2 branches with 1 carbon each. So 2 branches with 1 carbon each. One of them is attached to carbon atom number 2, and one is attached to carbon atom number 3. Now again, it's arbitrary choice. I could pick top or bottom. I'm going to put one on the bottom and one on the top, simply just to spread things out a little bit. It doesn't matter. You could put them all on the top. You could put them all on the bottom. But again, I just put them in different places, so when we start adding the hydrogens, they don't wind up overlapping with each other. So now if we add on the hydrogens, what we need to remember is each carbon always makes 4 bonds. Hydrogen always makes 1 bond. So this carbon right here is going to have how many hydrogens? 3. Because it's already bonded to 1 carbon here, so it needs 3 more hydrogens. This carbon right here is going to have how many hydrogens? Just one, because it's already making 1, 2, 3 bonds. It needs just one more hydrogen. This carbon here is going to have how many hydrogens? One. Because it's already making 1, 2, 3 bonds, and so on. So we go through here. I'll add in my hydrogens. We have an H3, H, H, H. This one here is going to be H2, and on the end it's going to be H3. On the top here we have an H3, H3. This will be an H2, and on the end an H3. So as you go the direction where you're building them, my recommendation would be first to just put in the skeleton showing the carbons, and then add in the hydrogens from there. Then one of the good confirmations you can do is to remember that the general formula of an alkane is always CnH2n plus 2. And if this is your general formula, then what you should be able to do is to figure out if this is the right number. So if we count the number of carbon atoms, this one's not working. I'll get that out of the way. Count the number of carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. Now we got this all right at the beginning. If we have 10 carbons, how many hydrogens should there be? 22. So then count in here to see if we have 22 carbons. Here we have 3. This makes 6, 7, 8, 9. That makes 11, 14, 17, 19, 22. So if those numbers match, and you were careful about making the number of bonds, you should have the correct structure. Any questions on this one? Okay, let's do the last one. You do the last one here now. Draw out the structure for whatever it is. 3-ethyl, 4-propyl octane. Remember to fill in your hydrogens. Let's go through these. First of all, the parent chain is going to have how many carbons? 8. So we write them in. 1, 2, 3, 4, 5, 6, 7, 8. How many branches are there going to be? 2. One of those branches is going to have how many carbons? 2. The other is going to have 3. The 2 carbon branches are going to come off of carbon atom number. The 2 carbon branches off of carbon atom number 3, and the 3 carbon branches off of carbon atom number 4. Put them in like this. So now, help me out as we go from left to right on these up here. Number of hydrogens will be H2, H2, and H3. Going across in the center, this is going to be H3, H2, H. How many hydrogens here? Just one. How many hydrogens here? One. This would be H2, 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 and H3. On the bottom, this is going to be H2, and this will be H3. Remember that in your text in Mastering Chemistry, this last one is often written as an H3C. It's really no different. It's just the convention that many organic chemists use. If you write it as H3C or CH3, it means the same thing. I've always written it like this. Your author and many organic chemists write it flipped around on the left-hand terminal carbon. Any questions on these? All right, next up, we're going to look at the alkenes and alkynes. So we'll go on to the next piece here. The alkenes. We should probably talk about those. We'll put a little piece in. These are your unsaturated hydrocarbons. Your unsaturated hydrocarbons are the alkenes and alkynes. The alkenes with an E-N-E suffix, these here have a carbon-to-carbon double bond present in the molecule. And the alkynes with the Y-N-E suffix, these here have a carbon-to-carbon triple bond present in the molecule. And when we talk about the alkanes, like we started with last week, the alkenes and the alkynes, your mnemonic is very easy. Remember, your mnemonic is a memory aid. So your alkenes are single bonds, alkenes are double, alkynes are triple. So if you learn them in alphabetical order, alkanes, alkenes, and alkynes, then they are single, double, triple bonds. Now in this class, that's all we go into. If you were to go into organic chemistry, and the reason why they have a whole year on organic chemistry is that you can have like dienes, you can have diines, you can have eneines, and if it's a diene, it's going to have two carbon-to-carbon double bonds. A triene would have 3 carbon-to-carbon double bonds. There's all sorts of possible arrangements they could have. We aren't going to be spending time with that in here. We're learning the very basics of these things. But since we did start the class today talking about the fact that unsaturated hydrocarbons aren't saturated with hydrogen, notice what happens here if we take these that have the carbon-carbon double bonds or triple bonds. If we have a double bond, if we open this up, how many more hydrogens can we fit in here? 2 more. If we open up the double bond in here, how many more hydrogens can we fit in?
2 more.
2 more. So every time we put in a bond between 2 atoms, we are removing 2 hydrogens. And when we have a carbon-to-carbon triple bond, if I open this up, we can add in 2 more hydrogens. So if I open this up, we can put in 2 more hydrogens. So if we have a general formula for alkanes, we can also have a general formula for alkenes. And because these have a carbon-to-carbon double bond, and it has 2 less hydrogens than an alkane, we could say that the general formula would be CnH. How many hydrogens should there be in an alkene? If the alkenes were CnH2n plus 2, that an alkene must be CNH what?
Or 2n minus 2.
Almost. Because remember, if the alkenes were 2n plus 2, and one bond simply removes 2 hydrogens,
Oh,
just 2n, exactly. So this is going to be H2n. And then the alkyne, because this has a carbon-to-carbon triple bond, a general formula for an alkyne is going to be CnH2n What else do we need on this one? So we open this up. We now have a carbon-to-carbon double bond. We put it back here, a triple bond is going to take away how many hydrogens? 2. So this is going to be 2n minus 2. So if you learn that the alkanes are the H2n plus 2, the alkenes are H2n, then the alkynes are going to be H2n minus 2, as far as the general formulas go. Now the next question would be, is if this requires a carbon-to-carbon double bond, and this is a carbon-to-carbon triple bond, what is the fewest number of carbon atoms you can have in an alkene? What is the fewest number of carbon atoms you can have in an alkene? Can you have 1 carbon atom? What do you think? No? Can you have 2? Yeah, you can have 2. So we must have at least 2 carbon atoms. What's the fewest carbon atoms you can have in an alkyne? That's going to be 2 as well. So if we were to look at these two, here are the fewest you can have. So it's 2 carbon atoms is the fewest. If we were to now write general formulas for these, let's go ahead and write these out. A condensed structural formula for this first one would look like this. It's going to be H2C double bond CH2, or, and this is the way I write them, as CH2 double bond CH2. And if we were to write out this one right here, we could write it as HC triple bond CH, or we could write CH triple bond CH. So these are the 2 different ones that we're going to be looking at. Then when it comes to naming these, here's what the naming rules tell us that we need to do. And by the way, we're going to highlight this. In Chem 1020, which is what the course you're in, you're only going to be responsible for the straight chain alkenes and alkynes. And by straight chain, we're not going to talk about branching. Now, it is true, if you've gone ahead and looked at the Mastering Chemistry, that you have some branched ones that have been assigned in there. That's because Mastering Chemistry does not let me refine it anymore, so you may be on Mastering Chemistry asked for them, but when it comes to your exam, you will not have any branched alkenes or alkynes. You want to know what you're going to be responsible for on the exam when it comes to naming. Then look at this worksheet and look at the examples that we're doing here in class. So this worksheet that we passed out last week is the examples of the things you'll be responsible for naming, and there are not going to be any branched alkenes or alkynes in there. But here's what the convention says. It says to count the number of carbon atoms in the molecule, and we're going to write the name of the alkane that has the same number of carbon atoms. And if we have an alkene, then what we do is we drop the ane suffix from the alkane name and replace it with the suffix of ene. For the alkynes, we'll drop the ane suffix from the alkane name and we'll replace it with the suffix of yne. So, following those rules, let's first name the alkane that would have 2 carbon atoms. An alkane that has 2 carbon atoms would be Lauren, you got it?
Alkane with 2 carbons?
Yes. Ethane, right. So then if we have an alkene, then we change the name from ethane to ethene. And the name of this is going to be ethyne. So we have ethene and ethyne as the two names. So again, ethene and ethyne. So really your key to success here in organic chemistry is to learn those prefixes and suffixes. If you can count carbon atoms, you've made yourself halfway there. So naming the prefix or counting carbons is the first half. The other half is identifying the types of bonds that are on there. And so if you can do those two pieces, that's how we put together the names of our organic molecules. So this is ethene. Eth means two carbons, and ene suffix means we have the carbon-to-carbon double bond present. So from here, any questions on those two? So from here now, we're going to take the models that you built. And now, since I assume that you've looked and compared at other ones, I'm just going to go through these and grab them and see if we have, in fact, made some different ones. Any of them that are different than these two, which I think you probably have them. Maybe you have them all in the front row. This one is different. I'm looking at Simon's there. I think yours is the same as this one. Lauren, I think yours is probably different. Yep. So we'll take these here and we're going to look at them. These are 4 different molecules now that have the same chemical formula, which means that these are all what of each other? Same chemical formula, different structures. They're isomers of each other. So these are the 4 isomers of C4H8. And there's actually more. We didn't look at the cycloalkenes in here, but it turns out we can make a ring structure that has 4 carbon atoms as well. We're not going to spend time with them. So with double bonds, these are the 4 isomers we're going to have. Now, if we follow the rules of what I promised you in here, one of these we are not going to be responsible for naming. Which one are we not going to be responsible for naming in here? No. Right. So while we build this one, we're not going to be responsible for naming this on the exam. You may on Master Chemistry, but on the exam you will not. But let's just go really quickly and talk about what's different between these. What's different between these two?
The double bond is earlier in
the chain.
In the chain, and then that one's in the middle.
Exactly. So now, what we do here, just like if we have 4 people in this row right here, we're going to count slots or spaces. So if you have 4 people, how many slots are you going to have? 3. If we have 4 atoms, we have 3 slots. So we would say that this here is in slot position number 1. This one here is in slot position number 2. So now if we went about and named these, naming them, we first of all, remember we named the chain as if it was an alkane, then replace it with an ene suffix. So the name of this is going to be 4 carbons. What is 4 carbons? Bute. So this is going to be butene. This is going to be butene. This is also going to be butene. But then to distinguish between them, let's look at our rules here. If we want to distinguish between these, and where's my, there it is, to distinguish between these, then what we're going to do is we're going to locate and assign a number to the slot position of the double bond or triple bond, and we'll count in the direction that gives us the lowest number. We'll then place the number in front of the entire name, separating the number and the name with a hyphen. So if we were to name this one here according to that convention, this one is going to be called 1-butene. It's going to be 1-butene. So if we write this out, we would have 1-butene as the name. And then the structure for this one would look like this. We'd have CH2, then we put in the double bond, we have a carbon, Then we have a CH2 and a CH3. Remember, the ENE suffix tells us that this is an alkene. The other thing we need to remember is that the general formula for an alkene is CnH2n. So that's why we have C4H8. If you count the number of hydrogens in here, it looks like I forgot a hydrogen where? Right, yeah, right there. So I forgot the hydrogen in here when I wrote it out. So that's a good thing I reminded myself that it's CnH2n, because that told me right away that, oops, I forgot that hydrogen in there. That one belonging right here, and we're showing each carbon making the 4 bonds. Okay, any questions on that one? Okay, now we go to these two right here. Let's count the longest consecutive chain of carbon atoms in each one. 4 here and 4 here. Slot position in this one is 2. Slot position in this one is 2. Okay, but if you look at these are not the same molecule. What is different between these two? What's different between these two? It's the orientation around the double bond. If you look at this one here, we'd see that this orientation has these two groups on sides that are opposite of each other. If we look at this one here, we see that these two groups are on the same side of this double bond. Now, the reason why these are different from each other is that there's one feature of double bonds that is different than single bonds. One of the features of double bonds is you cannot rotate or spin them around. Whereas when we went to single bonds, one of the features of single bonds is you have this rotation, they can spin around. So while we might show them here as being on the same side and this one here on the opposite sides, this is the way that these molecules will always be behaving in 3 dimensions. They're always going to be spinning around. Sometimes they will be on the same side, sometimes they will be on opposite sides. Whereas when we have a double bond in here, rotation is prevented, so they are locked into these positions where they are on sides either opposite of each other or sides where they're on the same side as each other. So when we draw these out, here's how we go about drawing them out. And a carbon-to-carbon double bond backbone will always look like this. So when we draw out this carbon-to-carbon backbone, we draw it with a backbone that looks like this right here. And I'm going to show the two different ones here right now. We have the two carbon-to-carbon backbones in there. And now if we want to show this, where they go, we want to show how they're locked in sides opposite of each other. We put in the carbons here and here. And then the other way we could go is to show the two carbons on the same side. Now I could draw both of them up above, or I could draw both of these carbon atoms down below. Doesn't really matter where I do it. And likewise with these carbon atoms, I could show them on opposite sides. I did show them to you like this right here, but I could have just as well showed them to you like this, as long as they're on sides opposite of each other. So however you want to put it in, that's fine. And then what we're going to do is we're going to go ahead and write in the hydrogens. Once we do that, we put in the hydrogens right here and here, here and here. And then this one here is going to be a CH3. This one down here is going to be a CH3. This one down here is going to be a CH3. This one down below here is going to be a CH3. And then if we want to name these, here's what we're going to do. First of all, again, we have the parent chain, which in each one of these has those 4 carbon atoms. If it's a 4-carbon parent chain, we want to name them. Each one of these is going to be called butene. Butene. Each one of them has double bond located in slot number 2. So because the double bond is located in slot number 2, each one of them is going to be called 2-butene. But because they're different from each other, we want to distinguish them from each other. And according to this rule, it says if we have an alkene and the double bond is in any slot position other than the first, you must tell whether the alkene is a cis or trans isomer. If the chain builds in each direction on the same side of the double bond, we say it is a cis isomer. If the chain builds in each direction on opposite sides of the double bond, it is a trans isomer. So this one here, if you look at the double bond, are they on the same side or on opposite sides? They're on opposite sides. This makes this a trans isomer. So we would call this first one trans 2-butene. And here they're on the same side, so this is going to make this cis 2-butene. And if you've ever heard of, when it comes to fats, we're going to take a break here in just a bit and work on it, but when you've heard of fats, you've probably heard of trans fats. Last week we talked about saturated and unsaturated fats. That terminology comes from the carbon-to-carbon double bonds or single bonds. Trans fat also has a situation where when we have the double bonds located, the attachments across the double bond across from each other, we call that a trans arrangement. It turns out that we get those when we partially hydrogenate vegetable oils. If you ever looked at packages of cookies or potato chips or something like that, you'll see one of the ingredients on there is very often partially hydrogenated vegetable oils. And part of the reason why we partially hydrogenate vegetable oils is because if we'd have a vegetable oil in a cookie or in a potato chip or whatever else, one of the features of oils is that they are liquidy. And so nobody wants a cookie that's got oil dripping out of it. But it might be the reason why if you put a cookie on a napkin, you might see a small wet spot on the bottom, and that comes from some of that vegetable oil coming out of it. But when you partially hydrogenate it, what you do actually is you're solidifying it somewhat. And when you partially hydrogenate, vegetable oils have polyunsaturated fats in them. When they're polyunsaturated, they contain both cis bonds and trans bonds. But when you partially hydrogenate, what happens is that the cis bonds are more reactive than the trans bonds. And they're more reactive because of the fact that when you have these cis arrangements, like this here's a cis arrangement, remember that single bonds always spin around. If you notice what happens is that if we try spinning these around, they start colliding here in this cis arrangement. That's not a stable arrangement. So as a result then, these cis bonds tend to disappear, and the ones that remain in fats tend to be these here now, which when I spin these around, you'll see that these are not going to collide with each other. That makes this trans arrangement a lot more stable, and as a result, when you partially hydrogenate, you get rid of the cis and you leave behind the trans. And of all the fats, the ones that they tell you to avoid is going to be the trans fats. And part of the reason for that is that while naturally occurring trans fats are out there, they tend to be in animal fats, not in vegetable fats. And when you start getting a large concentration of these trans fats, that's not a very good healthy thing. If we do this last one right here, this last one I'll write down. This last one is not one you're going to be responsible for naming, but if we did name it or write it, we'd have a CH3. We see a C. How am I doing this? Maybe like this. Double bond CH2. And we'll have a CH3 up above. If we were to name this one, but again, you're not responsible for it, we wind up naming it something like this. We would call this one 2-methyl propene. But again, we're not going to be responsible for naming this. You can kind of asterisk that one there. So for ones that you are going to be responsible for naming, we come back to here. I'll do 2 examples with you and then we'll take a break. You can work on the other 2. Let's apply these rules. Let's apply these rules. So again, the rules we're applying are these right here for the alkenes and alkynes. So this is in your packet. Now, if we want to name this, the rules tell us we are going to count the number of carbon atoms in the molecule and write the name of the alkane. So we count the carbon atoms right here. How many carbon atoms do we have?
5.
We have 5. So a prefix that stands for 5 is pent. Because we have a carbon-to-carbon triple bond, this is going to have a suffix of -ine. This will be pentyne. And then the rules tell us next that we want to identify the slot position of the double or triple bond. This slot position is going to be slot number 2. So we call this one here 2-pentyne. Then if we go in the reverse direction, this parent chain is going to have how many carbon atoms? 8. It has a suffix of ene, which tells us double bond. So if we want the double bond, we're going to start by putting in this backbone feature. This is going to tell us that the double bond is located in the slot number 4. And it's going to have a trans arrangement. If it's going to have a trans arrangement, that means we're going to build on sides that are opposite of each other. So we start building like this. We're going to have 4 carbon atoms, 5, 6. We want to make sure that this remains in slot 4, so we count 1, 2, 3, 4. We have 5 carbon atoms altogether. So there'd be 6, 7, and 8. And then we can go ahead and put in our hydrogens. We'd have a CH3, CH2, CH2. Just remember that each carbon atom makes 4 bonds. And if you go through here, remember that because it is an octene with an ene suffix, the number of hydrogens is always going to be equal to 2n, where n is the number of carbons. Do I have 9 carbons?
Yeah, you added an extra.
Oh, did I count wrong? Well, see, I would have figured that out when I counted hydrogens, but thank you. So there's our 8 carbons. There we go. 1, 2, 3, 4, 5, 6. I have 10. Okay, 10 fingers in my hand. All right. So we count the number of hydrogens. How many hydrogens should there be in here?
18.
There should be 16 in here, right? So if we count 3, 5, 7, there's 8, 9, 11, 13, there's 16 hydrogens altogether. All right, let's do the next 2 here, and we'll combine this with our break. Let's resume at 9:15 today, unless you want to skip the break.